Good afternoon, everyone. Welcome to the 11th session, problem solving session in the course Chemical Engineering Thermodynamics. Week 11th topic is phase equilibria and stability. So, till now, what have we read is generally what are the equation of states for real for real gases or liquids for real one. And then then we discussed about mixtures of gases and mixtures like solutions, mixtures and solutions. These are the liquids and gases. And we have defined the residual property and excess properties also. And there are different equational systems for the residual and excess properties. Okay, and from there we derive different energy properties like the Gibbs energy, enthalpy, and volume, molar volume, and internal energy. Okay, and Helmholtz energy. So all these energy properties we can get from these equation of states. Later, we were discussing what will be the what is meant by phase equilibrium, and we defined. Okay, when we were discussing these things, we were defining the fugacity and fugacity coefficient. Okay, and similarly here, activity this is for the gas and liquid or whatever is any substance, and the fugacity coefficient is for the gases thing, and the activity coefficient in case of solutions. Okay, this is for the mixtures, gas mixtures. This is for the liquid solutions. So if this is vapor liquid equilibrium, okay, there is one liquid here and vapor here. There can be any number of components in the liquid and in the vapor, whichever is miscible in whichever phase. There will be that like that. Okay, assume alpha, beta, gamma, all these components are there here, alpha, beta, gamma, and so on, delta, like that. Okay, in liquid and vapor, and these both are in equilibrium. Okay, then when are these phases in equilibrium means each species fugacity in the liquid, each species fugacity in the vapor should be equated, okay, in the mixtures. So that is what we have done here. And the liquid one can be elaborated as the mole fraction into activity coefficient into its fugacity individually when it is not in a liquid solution. Okay, and similarly for the vapor, mole fraction into the total pressure into fugacity. So generally how this fugacity coefficient is defined is the fugacity of the mixture in the mixture by fugacity when it is an ideal gas mixture. Okay, when it is ideal, then it is YIP, right? That's how. If normally also you say Fi of the gas by its normal pressure. The means YI is 1. Okay, like that. This is for the mixture. This is phi I cap if I define like this. Phi is this. Okay, like that. So and this Fi liquid is represented by phi I sat into pi sat into this exponential term. This is called as the Poynting correction factor. Okay, and this is mostly equal to 1 because assuming the pressure is near the saturation pressure. So exponential of 0 is 1 in that way. Okay. And these 5 sat and psi at the are at the saturation temperatures. Okay. Means at that temperature, what will be the pi saturation? Okay. Like that, if you see, this is the term when it is a vapor liquid equilibrium. At moderate pressures, the phi vapor can be neglected, can be assumed to be 1. And anyway, as I told, the Poynting correction factor can be assumed to be equals to 1, along with phi sat is equal to 1 and phi vapor equal to 1. And when it is an ideal gas and ideal solution both, this is at moderate pressure, this gas phase turns into ideals. That's why this phi I cap and phi I sat are assumed 1. And later, Raoult's law assumes ideal gas and both ideal solution. So gamma is also assumed to be equal to 1. So considering this, last time we was discussing that there will be few equations which we have to solve in MATLAB. So I could not attach that MATLAB solving in the last time, but this time I'm showing you like I'm solving few questions from the last previous assignment. I will be doing that at the end of the session. Then I'll be showing you how to solve in MATLAB different equations. Okay. And so now coming to a binary mixture, as we discussed in the last week, these are the variables, temperature, pressure, and the mole fraction. Okay. And these are both the Raoult's law. And these are the mole fractions. And these are Antoine equations. So generally, this saturation pressure, these are the empirical equations for all different compounds. People like scientists have found the Antoine constants for these. Okay. So for each compound, you can find the saturation pressure using the at a given temperature, where these Antoine constants are found using by doing the experiments. Okay. For each compound, for different compound, you will have in the appendix of any textbook, basic textbook, you can find these all. Okay. So now you can see here that what all variables here are the temperature. Okay, I'll show from the beginning this pressure. Okay, x1, y1, x2, y2, and temperature. These were the 6 we were mentioning earlier. Now later, this P1 sat, P2 sat are the additional variables. So now we have 8 variables and 6 equations. So we should know at least 2 of the variables to solve the system. Okay. So that is what is generally defined as degrees of freedom. Degrees of freedom means what is the minimum, minimum number of variables you should be knowing to solve set of equations. Okay. Generally, it is defined as 2 minus pi plus n, or you can always say f is equal to c minus p plus 2, where c is number of components, p is number of phases, and this is additionally 2. Okay. Now, There can be different types of calculations, like as I said, there should be at least two things known. If I know x1, for example, and temperature, anyway, x2 is known. Okay, that you know, right? X1. So that is one of the equation, right? So x and t are known. So anyway, t is known. Okay. So I would say bubble pressure and dew pressure. Okay, I'll discuss about this problem. Bubble pressure means the pressure at which the first bubble will come, arise. Means the boiling thing we are finding, okay? Means I know there is a liquid and I have made a solution, liquid solution with some concentration of some benzene and toluene, for example. Okay, and I am fixing this concentration initially, and I know some temperature, room temperature, it is there. Okay. Now, what temperature I should go to? No, at the given temperature only, if I have, okay, I am increasing it to some 50 degrees Celsius, imagine. Then what will be the pressure of the vapor forming and what will be the mole fraction of these compounds in the vapor? You can find some sort of application in this, like from the beginning I'm saying these examples, like I have, okay, I am storing some solution, okay, some ethanol solution as well, okay, with water mixed in it. Now, how long at a given temperature I am storing, room temperature, but outside the temperature can go to, can increase based on the seasons, right? Now it can go till 40 degrees, assume. Then at 40 degrees, what can be the maximum pressure build up in the container, so that at least my container should be able to handle that much pressure, right? So like this, generally we have containers. I have some liquid, okay. I will not store completely till here, okay. Anyway, I'll be filling around some 80%, and I will leave this for if with increase in temperature there is some vapor forming here. So what will be the pressure of the vapor? So my material, this container should be able to handle that much pressure, and also I should not lose so much ethanol into this vapor, right? So uh, okay, basic requirement, pressure requirement, I'm telling you, okay? So from this, you can find this. These are all 6 variables. Inside P1 set and P2 set, anyway, you will be finding for all the equations. You need it for Raoult's law, right? So you will use Antoine equations for the Raoult's law anyway. So what you want to find out intensive properties are this Y, X, P, and T. Now, when temperature is known already, it will be easy for me because like normally calculation I can do by knowing the temperature. I can find the P1 sat and P2 sat. Right? I have known these. Now, I already know X. Now I have found P1 sat. I don't know Y1, Y2, and P. Right? Now, if I sum up these A and B, what I have is Y1P plus Y2P equals to X1P1 sat plus X2P2 sat. Right? Now, if I see here, P into Y1 plus Y2 equals to, so X1 P1 sat plus X2 P2 sat. Now we have this equation D, so this equals to 1. Now I know all these variables. No, so I have found P is equal to something, right? Now I can find Y1 is equal to X1 P1 sat by P. I know all these variables. So this is very simple when you know temperature already. Okay. This is one situation. But when these conditions are there, when you know pressure, here, you know pressure. Okay. Assume you know X1 also. You don't know P1 sat and you don't know Y1. Even if I'm adding, okay, I know pressure, but I don't know P1 sat and P2 sat, which are in terms of temperature here. I don't know temperature here also. So how will I solve this? So what will I do is generally I'll just in this case iteration is needed. Okay. What I'm saying is I'll give some guess temperature. Okay. So mostly, yeah. So I'll give this guess temperature. From that, I will find PI sat. Okay, for both the compounds. I mean, okay. Sorry, there is a lag from between what I'm saying and what I'm writing. This is because of the internet connection here. Please excuse me for that. Okay. So I will find PI sat. Now I will insert this PI sat in the Raoult's law. In Raoult's law, what do we have? Now I know PI sat from the guess temperature. X I know, assume. P I know. X and P I know. Okay. Now I will find Y1 and Y2. So I am discussing about this problem. Okay. Upper temperature. X and P I know. PI sat I have found from the guess temperature. Now I will find Y1 and Y2. And what are we what should we check? We check here. There is one more equation, this D. Y1 plus Y2 is equal to 1. So now I will be checking some C is equal to C means check variable. Check variable I'm checking. Okay. C is equal to Y1 plus Y2 minus 1. Now if C equals to 0, stop. Not equals to 0, guess temperature again. Okay. Guess T again. How will I guess temperature? So there are few changings. Okay. That is Newton-Raphson method is there. So to make it simpler for you people, in MATLAB, for given, like generally if it's linear equations, how will you solve linear equations if it's there? Ax is equal to b, like this we will be solving for linear. But if it is like completely non-linear here, right? See, x and y are related. Okay, normally. But x, y and p are multiplied here because these are variables and x and p are multiplied. This is the logarithm is there, exponential thing. Okay. And this is division is there. These are not linear in way. These two are linear. I agree. But these four equations are not non-linear. Okay. So that's why we have a function solve. I've solved, where I give the equations and the initial guess. Okay, and it will solve for f is equal to 0. Okay, so this is what we have discussed till now in the last week. Now we'll be looking at what we are discussing this week. So when the coming to the discussion of vapor liquid equilibrium for a mixture, Fi cap vapor is equal to Yip phi I cap vapor. So here this gamma I. Okay, sorry. Okay. So we should equate Fi cap vapor equal to Fi cap liquid. Okay. Now discussing about this Fi cap, what will be the expression for Fi cap vapor? It is generally Yip into phi I cap vapor. Okay. Right. We have expressions for this phi I cap vapor. You remember, right? Ln phi is equal to this Margulis equation is there, Wilson's equation there, NRTL equation. So all these equations are there for ln phi and ln gamma. Okay. These are models. Now, if it is an ideal gas, then phi I cap vapor is equals to 1. That's why we are neglecting it. When it's a pure species, the mole fraction of Yi is completely equals to 1. So that is also neglected. And this is a real gas, right? So that's why this phi I vapor will be there. So it is, hat is there, then it is a mixture. If hat is not there, it is single gas. Okay. And if it's a pure ideal gas, then this phi I also equals to 1. Coming to the liquid phase, how will you find this? Mixture of species, as we have discussed here. Okay. But anyway, this exponential into Vi liquid P minus Pi sat by RT. This is the Poynting correction factor, which has been neglected here, equals to 1. Okay. Now coming to the ideal gas-like behavior. Sorry, ideal. Yeah. When the gas is ideal, then this will be phi I sat equals to 1. And mixture ideal solution is there, then anyway you know that gamma I is equal to 1 here. So what we have been discussing till now is Raoult's law. Okay, this is a basic law told this empirically only. Now, one more law is Henry's law, where your gamma I into Pi sat into phi I sat into Poynting, all these things are covered by the Henry's constant. And there are values for each compound. Okay, values for the Henry's constant. You have in the textbooks. Right? Okay. And when it comes to the pure species, anyway, you know, Xi is always equals to 1. And if it is ideal vapor, this phi I equals to 1. That's why Fi liquid is equal to Pi sat for a pure ideal vapor kind of compound. Later in this week, Professor Gumma has discussed azeotrophs. Okay, we have detailedly discussed all these things. But in this session, when it comes to problem solving, we'll be dealing with small problems where like it's more like kind of questions which are asked in the competitive examinations. We are dealing with that, but not only for that purpose. We are trying to cover the conceptually everything here. Okay. Now, when it comes to the azeotrope, what condition we have extra is xi is equals to yi. This is like a restriction equation where you are equating this xi and yi. So you're reducing the number of variables, right? Now, coming to the stability of a binary liquid mixture, we have discussed, sir has discussed this, 2 square of delta G by RT by dx1 square is greater than 0 at constant temperature and pressure, right? And then not only vapor liquid equilibrium, there are liquid equilibrium also. You might be you might have studied this liquid extraction, right? So later, for chemical engineers generally, people teach in the mass transport system or in the designing things or separation processes or industrial processes. You will be reading about absorption, okay, and distillation, liquid extraction. There are so many things like, okay, other processes are also there, crystallization, and okay, I forgot a few more. So here, what they do is distillation. There is a liquid mixture, and you want to separate the compounds in this. Okay, liquid to vapor and liquid. Liquid mixture to liquid and vapor. In absorption, there is some vapor flowing. Vapor flowing. And also there is some liquid here. And this vapor gets absorbed into the liquid flowing down. Okay. This is the absorption. And coming to the liquid extraction, there is, for example, alpha and beta. And there is a liquid mixture, okay? And we will have some gamma here. If I bring this in contact here, this beta splits into the both phases. So, like, which is like, there will be an equilibrium value for the mole fraction of the beta in alpha phase and gamma phase. So that is like liquid equilibrium. Okay. That is like extraction. If you generally have two compounds, that is what is discussed here. For the first phase, alpha phase, X1, alpha 1, X1 and 2 are the species. Okay. Alpha and beta are the phases. So these here relations you have when it is liquid equilibrium. And furthermore, you have vapor, liquid equilibrium for partially miscible liquids. Okay. And sir has discussed these all things. Now we'll be going through some questions here. So, coming to some questions here. For a system in equilibrium at a given temperature and pressure, the entropy must be a minimum. No. No, because generally entropy tries to be increased. Like it is increasing always. And the enthalpy must be minimum. No. But internal energy, no. The Gibbs energy must be a minimum. Okay. Fine. The necessary and sufficient condition for equilibrium between two phases is condition of each component should be same in the two phases. The temperature of each phase should be same. So this is not correct because this will be thermal equilibrium. The pressure should be same in the two phases. No, this will be physical equilibrium. So this is not correct. The chemical potential of each component should be same in the two phases. So what we write is we equate fugacities, okay? Fi in alpha is equal to Fi in beta. So this is the correct one. Condition of each component should be the same in the two phases. Okay, chemical potential of both the phases should be equal. mu1 is equal to mu2, not of each component. Okay, right. So that was a tricky question there. Third question, if the heat of solution of an ideal gas in a liquid is negative, then its solubility at a given partial pressure varies with the temperature as. So here it is given heat of solution, that is delta H solution. So it is similar to delta H reaction when we are like solubility is happening, okay? Making of a solution is happening, then this is a reaction. So that is negative. It implies the making of solution is an exothermic reaction. So it implies as we increase temperature, for example, that is not favored by the exothermic reaction. So the reaction is decreasing. Okay, the reaction is not favored. It implies the solubility is decreasing. So solubility increases as temperature increases. No, it is not correct. Solubility decreases as temperature decreases. Yes, this is what we have discussed. Solubility is independent of temperature. No, no, that's not right. Depending on the Gibbs free energy. No, this is depending on the enthalpy change of the reaction. Okay. Next, saturated solution of benzene in water is in equilibrium with a mixture of air and vapors of benzene. And water at room temperature and pressure. Okay. Mole fraction of benzene in liquid is Xp. Okay, here XP is there. Here, solution of benzene and water is there, XW. Here, benzene and air is there. Okay. That is a like water vapor only, right? Here also we will be having. So how do you generally write the partial pressure of benzene in the air vapor mixture is PB is equal to YB into P, right? This P, now this is equated to XB into PB sat. This is like we are equating the assuming ideal gas behavior. This phi I sat is phi B is neglected here. So we are equating the few gaseties here. Okay. So this is equals to XP into P vapor. So V is vapor. Okay. Next question. So all these are on based on the phase degrees of freedom equation. Okay. For a single component, two-phase mixture. So F is equal to C minus P plus 2, right? So single component 1 minus 2 phase 2 plus 2 equals to 1. So number of independent variable properties are 1. Right. At a given temperature and pressure, a liquid mixture of benzene and toluene is in equilibrium with its vapor. The available degrees of freedom is or are. So this is a liquid vapor equilibrium. Generally also we have discussed that at least two variables should be known. So we will see the same thing here now also. F is equal to components, benzene and toluene are there. So two components minus two phases, liquid and vapor is there, plus 2. It will be giving us 2. So the degrees of freedom are 2. A gas mixture of three components is brought in contact with the dispersion of an organic phase in water. So coming to the gas, three components. Gas mixture, okay. And come to the liquid solution. This is a dispersion of organic phase in water. So dispersion, generally dispersion means this bubbles. So one phase, one compound will be as bubbles, which is uh, dispersed phase, and this is continuous phase. Okay. So this is a dispersion generally called. So dispersion has two compounds, right? Water and the organic phase. Now, what is the degrees of freedom? F is equal to completely 5 compounds, 5 minus how many phases are there? So this is a gas mixture, phase 1 is there. And in this also, as I told, dispersion, this is one phase, this is one phase, two different phases. So completely 3 phases are there plus 2. So what we get is 4. Okay. This one. Next, the number of degrees of freedom for an azeotropic mixture of ethanol and water in vapor liquid equilibrium is. So what we are discussing till now, C minus P plus 2, this is like a basic equation. The full equation is C minus P minus M minus S plus 2. Okay. Here, M is number of independent relations. This is number of restrictions. So as I told you earlier also, in an azeotropic mixture, we have Xi is equal to Yi, which is a restriction. So here in this case, we have F is equal to number of degrees for ethanol and water. So 2 compounds minus 2 phases, okay? In vapor and liquid equilibrium, they are saying, so 2 phases minus this S is there, number of restriction is 1 plus 2, which is equals to 1. So only 1 degrees of freedom is required. So if you know at least one, like temperature, okay? This is a combination of ethanol and water. If I know what is the temperature here, I can tell what is the mole fraction in liquid, what is the mole fraction in vapor, and also what is the pressure. All these things I can tell from only knowing one temperature here. Right. Assume that benzene is insoluble in water. The normal boiling points of benzene and water are 80 degrees Celsius and 100 degrees Celsius respectively. At a pressure of 1 atmosphere, the boiling point of a mixture of benzene and water is. You can see, is it it will be like PBW less than PB less than PW. Okay. So this will be the correct. If TA and TB are the boiling points of pure A and pure B respectively, and TAB is that of a non-homogeneous immiscible mixture of A and B, then as written earlier also, this will be less than both of them. Right? In a binary liquid solution of components A and B, if component A exhibits positive deviation from Raoult's law, then components B. So generally, positive deviation, what do you mean by that? For assume at this temperature, at a given temperature, P vapor pressure will be there. But if positive deviation is there, P prime will be greater than P. So more vapor pressure will be there. Okay. So that is general understanding. Now, one component, one of the component B, A is exhibiting positive deviation, then component B also exhibits a positive deviation. Well, for a binary model, non-ideal A-B mixture exhibiting a minimum boiling azeotrope, the activity coefficients must satisfy. So as I explained, this is minimum boiling azeotrope, right? Means okay, you can say so like this is there, right? At a given pressure. So generally for getting this much vapor pressure, you have to boil at 100 degrees, assume like that. But now you will get that much vapor pressure at 70 degrees only. So that is called as minimum boiling azeotrope. Okay. Like the boiling point is decreasing. So this happens when the positive deviation is there. So positive deviation means both of them is greater than 1. The vapor pressure of water is given by one of the Antoine equation, where here we don't know what is the value of the Antoine constant A. Right. Then the vapor pressure of water in atmosphere at 50 degrees Celsius is approximately. So generally it is given water. We know that at 100 degrees Celsius, 1 atmosphere is the vapor pressure. So when we find out ln 1, assuming this is in atmosphere only, this equation is given in equals to A minus 5000 by T. The temperature is 100 plus 273.15. When you solve this, is ln 1 is equals to 0. So A is equal to 13.39. Okay. Now Psat at 50 degrees Celsius equals to exponential of 13.39 minus 5000 by T. T is 50 plus 273.15. Okay. And by calculating, we are getting this as 0.126 atmosphere. So this is equals to 0.13. Next, the vapor pressures of benzene and toluene are 3 and 4/3 atmospheres respectively. A liquid feed of 0.4 moles of benzene. So X is known here. Psat is given. Means anyway, the temperature is known. Okay. So this is a problem where X, T are known. And we are asked about the Y. So as I told you earlier, we do Y1P plus Y2P is equals to P equal to X1 P sat P1 sat plus X2 P2 sat, and this is equals to here 0.6, okay, 0.4 into benzene. Benzene has 3 plus 0.6 into 4/3. And how do you find y1? Y1 is equal to X1 P1 sat by P. Okay, right? So when you insert this P here and find out, you will find y1 is equal to 0.6. An equimolar liquid mixture of species 1 and 2 is in equilibrium with its vapor at 400 Kelvin. So X and T we are knowing here. At this temperature, the vapor pressures of the pure species are P1 sat, P2 sat. So P1 sat, P2 sat are given anyway with like instead of giving the Antoine equations, the P1 sat and P2 sat are given here. Okay. Assuming the Raoult's law is valid, the value of y1 is. So y1 is equal to, as we found last time also, P1 sat by total pressure, which is given by X1 P1 sat plus X2 P2 sat. Okay. Now, by inserting values here, you will be getting equals to 0.6. Right. A liquid mixture contains 30% O-xylene, 60% P-xylene, and 10% M-xylene. And all these percentages are in weight by weight. P, M. Okay. 0.3, 0.6, 0.1. This is like a mass fraction. The mixture, okay, we'll go through the options. The composition of the mixture in % by volume is this. Okay. So, when it comes to volume, we need to discuss about the density of the each compound. So, what are these? Generally, these are structural isomers, and because of the structure, the density of each of the compound is different, right? So that's why their volumes are different. So we have to find out what like the percentages won't be same here. Okay, that's the composition of the mixture in mole % is what? So to find out the mole percent, first we need to find out what is the total number of moles. Okay. So what is generally xylene? C6H4 and 2CH32 attachments will be there. And its weight as 106 kg per mole. So assume it's a 100 kg thing. Then this is 30 kg, 60 kg and 10 kg. Okay. So how many moles are there now? 100 kgs per 106 kg. This is the molecular mass equal. This is the total number of moles. Now, uh, if you find out the number of moles of NP equals to 30 by total number of moles are 100 by 106. This is the number of moles. Okay. Sorry. This is 30 kgs. So total molecular mass is 106, right? So 30 by 106 is the number of moles of P. O. O. And similarly for this, it would be 106. So what would be the mole fraction will be there is XO equals to 30 by 106 by total number of moles is 100 by 106. So which is again, what is it? 0.3. So similarly for the other components also, it will be equals to 0.3. This is X. This is weight fraction. This is mole fraction. 0.6 and 0.1. The composition, the mixture in mole percent is 30, 60 and 10%. The mixture contains optical isomers. No, because these are structural isomers. The mixture exhibits an azeotrope. No. So wrong. Okay. Going to the next question. An equimolar mixture of benzene and toluene is contained in a piston or cylinder arrangement at a temperature T. Excuse me, for 1 minute, okay? Okay, so an equimolar mixture of benzene and toluene is contained in a piston cylinder arrangement at a temperature T. What is the maximum pressure below which its mixture will exist as a vapor phase alone? So generally, what we have, so we are talking like at a given temperature. The temperature is fixed. So we have pressure profile for a vapor liquid equilibrium like this, right? Pressure in X and Y here. So what they are asking is for a given temperature, what is the pressure? The vapor pressure is the minimum pressure where this vapor will only be there, only vapor. So this is liquid and this is the vapor side. And this will be something like liquid plus vapor, right? So here we have already equimolar mixture of benzene. So we are considering this is Y is given here. So we have a general equation that is XA plus XB equals to 1, right? So satisfying that, we have YAP by PA sat plus YBP by PB sat equals to 1. So T and Y are known here. And so we are using the XA plus XB equals to 1 equation. And B and P sat and PB sat are given as, so benzene and toluene. So I am assuming A is benzene and B is toluene. Okay. 0.5 is both same. So 0.5 into pressure. That is what we have to find out is given, and 1 by PSAT is 1530 plus 1 by 640 is given as 1. So now we find P is 2 by 1 by 1530 plus 1 by 640. Now, on calculating, we find it as 902.4 mmHg. So these all are given in mmHg, right? That's it. Right. So in this, what was the type of the problem? What is the maximum pressure below which this mixture will exist as a vapor phase alone? Means when will the condensation start? So we were finding the dew point here. Okay. So we were discussing right there when T and Y is there, dew point problem is there, where you have to find the X and T. Now you can find the X also. The XA equals to, we know 0.5 into pressure, which we have recently found 902.4 by PSAT. This is 1530, right? Which is equals to 0.3. Coming to the next question. Determine the mole fraction of methane dissolved in light oil at 200 Kelvin and 200 bar. So T and B is given. Henry's law is valid for the liquid phase, and the gas phase may be assumed to be an ideal solution. So ideal gas is there. So phi I will be equals to 1 everywhere. At these conditions, general equation what I have is YIP to phi I equals to XI HI. So anyway, they have given the fugacity coefficient here. So Yi of the methane is there. So 0.95 into pressure is given as 20 bar into 0.9 is the fugacity coefficient equals to Xi, which is not known, into the Henry's constant, which is 200 bar. So from here, we find out that X is equal to 0.085. Okay. Next question. A mixture of A and B conforms closely to Raoult's law. The pure component vapor pressures PA sat and PB sat in kilopascal are given as this. So this is Antoine equations. If the bubble point of a certain mixture is 76 degrees Celsius at a given total pressure of 80 kilopascal, find the composition of the first vapor that forms. So temperature is known and P is known. So this problem is somewhat different from what I have discussed earlier, like 4 types of problems. Here T and P are known, and we have to find out the X and Y. Okay. So consider one of the equation like sigma x is equal to 1 or sigma y is equal to 1. So now I am considering sigma y is equal to 1. So I will be expressing y in terms of x. Okay. So YA equals to XA PA sat by P. Okay. So what all do we have is first XA, I don't know. PA sat and P I should be known. So pressure is given as 80 kilopascal. PA sat I have to find, okay, at the given temperature, right? So T in degrees Celsius is written here. So already, so that temperature, if I use here, the 76, by calculating the ln PA sat, I'll find, and PA sat is equal to exponential of that term and is given by the value 85.9 bar. And from here also, PB sat is given by 43.3 bar. Okay, right. So that is there. and YB equals to XB here can be expressed as 1 minus XB. Okay, into PB sat by P. And now I have YA plus YB equals to 1. It implies I have an equation XA into something plus 1 minus XA into something equals to 1. So this is a linear equation, and just simply solving you will find out that XA equals to P minus PB sat by PA sat minus PB sat equals to 0.86. And hence XB is also known 1 minus XA and equal to 0.14. Now we want to find out what is YA equals to XA, that is 0.86 into PA sat, that is 85.9 by total pressure, that is 80 kilopascal, and this is in bar. So I have done all those conversions here. So kilopascal you can convert it to bar and do this. Okay. Then you will be finding that equals to 0.925 and YB is equal to 0.075. Right. If for a pure liquid, the rate of change of vapor pressure with temperature is 0.1 bar per Kelvin. So rate of change of vapor pressure, delta P vapor. Sorry, I mean P sat by temperature, delta T equals to 0.1 bar per Kelvin. Now, in the temperature range of 300 to 350. If the boiling point of the liquid at 2 bar is 320 Kelvin, so 2 bar at 320 Kelvin, 1 bar at how much Kelvin? Okay, so this is 320 is in the range of 300 to 350. So this equation is valid here. So I am writing this as 2 minus 1 by 320 minus T equals to 0.1. And by solving, I'm getting T is equal to 310 Kelvin. Right. Sparingly soluble gas is in equilibrium with a solvent at 10 bar. The mole fraction of the solvent in the gas phase is 0.01. So, okay. So now a sparingly soluble gas is in equilibrium with a solvent at 10 bar. Okay, P is no. The mole fraction of the solvent in the gas phase is 0.01. So Y is equal to 0.01 of the solvent. So Y is known. At the operating temperature and pressure, the fugacity coefficient of the solute, this is solvent, okay? This is solute in the gas phase and is equal to 0.92, and the Henry's law constant R is equal to 1000 bar. Okay, assume that the liquid phase obeys Henry's law. The mole percentage of the solute in the liquid phase rounded to 2 decimal places is. So Raoult's law, we have YAP into 5 so equal to XA by right A of N XA into H. Right? Now A is the solute here. So we are solving for the solute, right? So that's why YA will be 1 minus 0.01 equal to 0.99. Okay. Therefore, what do we want to know is XA we want to know. So that's why XA equals to YA P phi A hat sat saturation by HA equals to 0.99 into 10 bar into 0.92. The fugacity coefficient by Henry's law is 1000 bar. So this gives us XA equals to 9.1 into 10 power minus 3. And since here the mole percentage is asked, 9.1 10 power minus 3 into 10 square equals to 0.91 and to the rounded to the 2 decimal places. Understood? Right. Consider a sealed rigid bottle containing CO2 and H2O at 10 bar and ambient temperature. So P is known. Assume that the gas phase in the bottle is pure CO2 and follows the ideal gas law. So gas is ideal, okay, and pure. So YCO2 equals to 1. The liquid phase in the bottle contains CO2 dissolved in H2O and is in ideal solution. So solution also ideal. Okay. The Henry's constant at the system pressure and temperature is 1000 bar. So it is written Henry's law is followed for the liquid. Okay. The equilibrium mole fraction of CO2 dissolved in H2O is. So how do you write YAP phi A hat sat, right? But this is equals to 1 because it is an ideal gas behavior equal to XA HA. So XA equals to YAP by HA equals to 1 into 10. P is equal to 10 by here, right? By HA. HA is given as 1000. So equals to 0.01. Right. Next question. A fractionator recovers 95 mole% of N-propane as the distillate from an equimolar mixture of N-propane and N-butane. The condensate, so equimolar mixture is given already here. So the condensate and recovery is 95 mole%. Saturated liquid at 55 degrees. So temperature is known. So Psat will be known. And the constants below are provided. You have to enter here. So if I find in propane, Sat, and P in butane, Sat equal to what? Okay. So we have found that 18.65. Hello. Chapter. So given as 18.65 bar, and this is given as 5.59 bar. Okay, you can compute this. Okay. Now, using Raoult's law, the condenser pressure is, so T is known and X is known. Okay, X is like X and B equal to 0.95 and X and B equals to 0.05. Okay. And hence, here you have to use in Kelvin, okay? 55 degrees into 328.15 Kelvin. Right. So X is known, T is known. So this is a simple problem as you know. So P you will find out as XA PA sat plus XB PB sat. So you can observe here that we are discussing mostly the binary systems only, because at this level of the course, we are going to deal with the binary systems only. The LLE is also like a binary system. VLLE comes with more than more compounds is also possible, but we are not solving them here because by hand binary system is easy to solve. That's why we are looking at it, and institutions also follow these things for academically. Okay, but of course in industries it's not all binary systems everywhere. Okay. So when you calculate this, you'll be finding pressure is equal to 17.999 bar. Okay. So equals to 18 bar. That is what is asked here. Okay, it's a pressure. Okay. Right. So this is all about week 11 questions. Now we want to discuss about the week 10 assignment. Okay. So what I'm saying here is, mm, majorly one is there. Okay. The first question is G by RT is 2x1 minus x1 square minus x1 cube with x2 is given. So what is asked here is activity coefficient of species 2. Okay. Gamma 2 is required. So when we have G by RT, we want to find ln gamma 2 is equal to G2 bar E by RT, which is equal to dou N G by RT by dou N2 at constant temperature, pressure, and N1. Okay. The one inside this you have to derive. So I will write here that what is this? NGE by RT equals to 2N1 minus N1 square by N minus N1 cube by N square. Okay. So and ln gamma 2 you will find out as N1 square by N square plus 2N1 cube by N square, which is equal to x1 square plus 2x1 cube. Now x2 is given, so x1 is equal to 0.6. When you substitute in this, ln gamma 2 will be equal to 0.792. Resultingly, you will find gamma 2 is equal to 2.21. One digit after decimal, so it is 2.2. Okay. And the similar thing is used in the next question. But here what is asked is gamma 1 infinity. Okay. Then I'm just writing down the solution here because anyway you people have to solve these. So you will get ln gamma 1 equals to 2 minus 2x1 minus 2x1 square plus 2x cubed. This is in the similar way that we have done in the first questions. Okay. Now what is gamma 1 infinity? Ln gamma 1 infinity is equal to limit x1 tends to 0 of ln gamma 1 is equal to 2. Therefore, gamma 1 infinity is equal to 7.39. Okay, these are two simple questions out here. Coming to the next one. We have here x1, x2. Okay, liquid mixture containing this much benzene and this much toluene is in equilibrium with its vapor at pressure. So X and P I have here, right? And it is given what is the temperature of the mixture. Okay, now what I'm saying here, this is what I was trying to explain you people, that we have 6 equations here. Okay, y1 plus y2 is equal to 1. And Raoult's law, 2 equations, that is y1p is equal to x1p1 sat, y2p is equal to x2p2 sat, and these 2 equations. Okay, so I'll be showing you a MATLAB code for this. Just give me some time. It's taking time to open, okay? Right. I'll be going through this only. So I have the code here, which is week 10 question 3 I'm discussing here. So if you are familiar with MATLAB coding, you might be knowing, or you can easily learn MATLAB coding also. So I'm writing. Okay, if you are exposed to C writing, C coding, then it is very easier for you. So CLC is the clear screen, whatever we have written, like this is a command window and this is a script file. So CLC is the clear screen. Clear bars is whatever if you have variables earlier. Okay, for example, I have x is equal to 5. I 2 like this. Okay. Now in my workspace, x and with the value of 5 will be there. So first, if I do CLC, what's happening? The command window is getting cleared here. This is the function of CLC. And clear vars, if I do, this x is equal to 5 will be gone here. Yeah, so it's gone. And close all. If I have something like plot already, okay. Plot 1, 2, 1, 2, 3. So if I have some plot here, and if I go for the entry as close all, then my plot will get closed. Okay. So closed. So right now, all these functions are for that. So here we have x and p no, and these are like initial conditions for the iteration. As I explained in the beginning of the video, please go through that. So okay, I'll explain now itself. So since the P is not known, so no, sorry, P is known, but temperature is not known. So temperature is not known, P is and PB sat, you will be guessing by using some temperature, okay? The variables are y1, y2, t, p1 set, p2 set. Okay. So I'm giving some guess temperature. Okay, in my function, I have written it as like I'm giving guess P1 set and P2 set also. But anyway, finally, it will be changed according to the equation there. So I'm giving some y1, y2 here, temperature 300, I'm giving as initial condition. So at the end of this function, like command, I'm writing a function here. Yeah. This is function f is equal to some function name of variable. So x1 is equal to 0.55. It's already given. X2 is 1 minus x1. P is equal to 0.7 bar. And y1, y2 are variables, first one, second one, third one, like I'm allotting like that. Okay, there are 5 variables, right? And these are 5 equations which are made to 0. So we are solving for them to become 0. So that's why LHS minus RHS is equal to 0, right? So that's how we put it them here. So this is LHS Y1P minus X1P1Z, which is RHS. So this should become 0. Similarly, these both are like roles law. These both are Antoine equations, and the last one is y1 plus y2 is equal to 1, that equation. So finally, I'm getting equations out of this function. How I'm solving it is fsolve. As I explained earlier, fsolve is used for non-linear equations. So at the rate of variable, this f of variable with some initial conditions which I have given here. So if I run this, so run section. So it is solved already. So if I go through the bar solve, so there is a lag because of the screen sharing. Okay. Yeah. So 0.65 is y1, 0.34 is 0.35 is y2. This is the temperature, which we have to find 339. 0.8 is P1 sat, 0.5 is P2 sat. So it's a very easy thing when you know the coding. Okay. So this is the one we are discussing. Okay. So we have found y1 is equal to 0.65. P is equal to 338, right? 338. Right. Next, infinite dilution. Okay, now here in this question, we have x comma t known and what is y, right? Gamma 1 infinity, gamma 2 infinity, all these things are given. So Margulis equation. So in Margulis equation, we have ln gamma 1 infinity is equal to a12. So that's how we find a12 is equal to 2.442. Similarly, ln gamma 2 infinity is equal to a21, so equals to 1.253. And then later you find what is ln gamma 1. is equal to x2 square a12 plus 2 into a21 minus a12 into x1. And you compute it to be 0.1624. So it's a like simple thing only here. So similarly, you find the gamma 2 and ln gamma 2 also. And upon simplifying, the gamma 1 is 1.17, gamma 2 is equal to 2.21. Okay. Later, you want to find the y, right? So y, using the Raoult's law, now you will have y1p is equal to x1 gamma 1 p1 sat. And the p1 sat and p2 sat are anyway given here, right? So gamma 1 we have found, p1 sat, p2 sat are given, x1 is no, and the pressure is anyway x1 p1 sat plus x2 p2 sat. So that is how you will find y1 equal to 0.6 and y2 is equal to 0.4. Okay, right. And coming to the question 5, this is Wilson's equation. Here you have y known, t known. Okay, y and t known. So it is very easy for you when t is known. And in Wilson's equation also, you have ln gamma 1 infinity is equal to 1 minus a21 minus ln a12 and so on. Okay, and similarly for the ln gamma 2 infinity. And you have to solve these both equations. You will get a12 is equal to 0.12, a21 is equal to 0.68. So I'm leaving all the calculation part for you people, because then you will realize how easy it is. Okay, right. So here also, and then later you will find ln gamma 1 is equal to some equations there. Okay, which contains x and gamma 2. So this is contains x, which is not known. So these are two equations, and one more is x1 plus x2 is equal to 1. This is equation 1 and 2, equation 3. And again, you will have Raoult's law, y1p is equal to x1 gamma 1 p1 sat. y2p is equal to x2 gamma 2 p2 sat. So anyway, here p1 sat and p2 sat are known. So what variables you have right now is gamma 1, gamma 2, x1, x2, and p. So these are the 5 variables with 5 equations. And similar to the last one, you have to solve these equations in the MATLAB and find out. Okay. Right. So thank you. That's all for today. Okay. And I hope you people are gaining good enough knowledge from these problem solving sessions. And please give feedback so that I can improve. And next week only we have week 12 session. And after that, we'll be having an extra session for 2 hours before just before your exams. So I hope people come out there and ask out their doubts. Okay. Thank you so much.